and see what comments are. Okay, there we are. So tell us about your lunar sample collection box.
Okay, so just gonna move to the next slide. So our problem was to design a lunar sample box that prevents dust and other contaminants from entering the storage cavity while allowing the astronauts with bulky gloves to insert and retrieve samples without compromising the sample. It has to maintain a traceable and reusable containment environment that withstands launch stress, the lunar surface environment, and potential robotic handling, all while ensuring strict contamination control and compatibility with existing mission interfaces. So then here's a little bit of our research. So for military, law enforcement, or home defense applications, specialized containers offer unique features for organization security and access. Then there's the tactical cases, which are those made by Securelt. They may feature modular interiors, adjustable storage grids, which allows for flexible organization of rifles, shotguns, and other tactical gear. Then there's Safe in a Box. The Fast Box from Securelt is an example of a low-profile storage container designed for discrete, fast access. Then GSA-approved weapon containers designed for military and government use. These heavy-duty containers provide the highest level of security for weapons and ammunition storage. And then takedown cases for modular rifles. Takedown cases store the firearm in a disassembled state, providing a more compact and secure transport solution. So those are kind of the things that we took into account when designing our box. So then we have some of the summaries for the features of the different needs, like the material and protection, interior security, portability. And then major types of packing foam include polyurethane, expanded polyurethane, cross-linked polyurethane, and expanded polypropylene.
Yeah, I think you're right.
Other variations, anti-static, custom cut, and charcoal foam are also available for specialized uses. So then we have some of the different packing grade materials, and common types of packaging foam, like polyurethane, well, the stuff that I just listed. So then we have a little bit of history. The Apollo moon boxes, which include the airtight containers for lunar samples and the larger Apollo lunar surface experiments, have to contend with significant technical issues. The main challenges were weight constraints, thermal control problems, the abrasive and clingy nature of lunar dust, and issues with sealing the boxes under difficult conditions. CDC requires multi-layered or triple packaging system for the transport of hazardous biological materials, especially for air travel. These guidelines apply to infectious substances and are determined by their risk classification category A or B. All packaging must be marked and labeled in accordance with federal and international transportation regulations.
So for the criteria, if what we need block dust and contaminants from getting inside the sample area. Keep the sample in good condition, meaning like the temperature, air pressure, smells, and then be easy for it to be easy to use with astronaut gloves. Have strong seals that don't wear out and can handle launches and rough landing. Show exactly where samples are and prove no tampering happened. Work with other mission equipment and docking points. Prevent any harmful contamination and follow safety rules. Be reliable with backups and clear failure ideas, and be easy to test in labs.
Constraints or problems that we are trying to avoid. Safety is our top priority. It must not hurt astronauts or gear. heavy, quick safety checks or so like or focus regularly on size and weight
Sorry,
and small
can
effort to
you
carry
can you
and
stand a
lift.
little closer to the microphone? It's you're a little muffled there. Thank you. Go ahead, keep going.
State. I'm sorry. Environment. Extreme temperatures, vacuum, lunar dust must endure all these conditions for dust protection and must keep dust out from moving parts and samples. Reliability, it should work with little maintenance and clear failure signals. Safety keeping, samples stay safe and are known where they come from. Deployment, it must be easy to use and set up by all people. And materials, radiation and cold resistant, and use safe grade space parts to ensure it works in their environment.
So we kind of developed and proposed different designs, but the one that won was this here. So basically on the little rods that you can see on the lid, on the inside of the lid, they are going to have plastic sheets. And I don't know if you can see it very well, but on the main container, the red portion, there are little spikes. And when you close the container, the spikes are going to catch on to the plastic, onto one of the plastic sheets. And when you open it, there's going to be the layer of plastic on top and the layer of plastic on the bottom. So when you put the sample in and close the box, we're thinking of like some sort of heating system to heat the sides so that they can seal, and there's no need for any sort of like vacuum because space is a vacuum. And then the spikes will then rip off the top and bottom pieces of plastic, and then it'll fall into the main compartment. And then we also have these large handles so that the astronauts can hold the box and operate it easily.
So this should be completed once your prototype is completed and we spent like a day evaluating our prototype. We checked all the requirements, limitations stated.
You're done with the design.
Okay.
It's okay, we can get feedback.
Yeah. No, I like that you're following the template, which is really cool. And I was listening carefully to your what you needed, your criterias, and I'm glad you thought of one of them, which a lot of schools haven't, is know where these rocks that are in that container came from. So somehow to label the container or whatever. And I was also very interested in your that you did some research on biological containers. Because those have to be really safe. Do you ladies think that there could be possible biological something alive in your rocks that the astronauts would be putting in your container?
Potentially.
Yeah.
Yeah, that's interesting. So I'm going to let Dave talk on this, but it sounded like you had a very unique way of closing and sealing that container. I'm not quite sure I understood it. So maybe Dave, do you understand what they were talking about?
I want to try to clarify, and my apologies, but your voices are a little bit muffled to me, so I'm having a little trouble hearing you clearly. If I understand it correctly, your internal mechanism is designed to somehow pierce the bag once the box is closed. Is that correct?
Yeah.
Okay. I would recommend that you keep the material inside the bag and sealed as well, because actually that will give you another layer of potential protection of the samples. So if we back up for a minute, um, I want you to understand that the primary design objective is to allow samples to return to Earth in the exact same state as they're collected on the moon. When the astronauts open these boxes up and put their samples in, they're obviously in a vacuum, right? The surface of the moon, there's no atmosphere. The issue with the Apollo samples was many of the seals failed and air was able to leak inside of the sample boxes. And since the air was able to make contact with the surface of the dust or the rocks, it essentially contaminated it with our environment. What the scientists want to be able to do is assess the pristine chemical composition of these rocks. So they're going to be brought back in these boxes. They're going to be put into a vacuum chamber and then opened back up. So the idea of actually having more than one layer of containment is an excellent idea. And I would recommend that you not pierce that you just have them sealed up in some way and placed inside the box, and then the box becomes an additional layer of containment for the samples.
Mm-hmm. Can you go back to the picture of your rocks? Because I got the impression you weren't piercing the sample, you were piercing the box.
No, just the sides of the plastic so that it can fall off and into the box.
Yeah. And again, I think it's good to have that layer of containment. I just wouldn't pierce it. I would recommend against doing that. That will actually simplify your build a little bit. Okay. What material are you planning to make your prototype out of?
Bring it to life. Just thank you.
We were thinking of using like a cardboard to bring it to life.
Okay. An initial design of your prototype in cardboard would be good, but I want you to be thinking as well about any testing you can do that will confirm that you have a good tight seal and you can protect the internal environment of the box. Now, in reality, it's not practical to think that we're going to be able to do anything in like a vacuum chamber. Even if your school were, for instance, I wouldn't be surprised if your chemistry or physics teacher probably has a bell jar and a vacuum that they can pull a small vacuum for experiments and demonstration. But putting something the size of a box in there would be difficult. So what we're recommending as a way of proving the efficiency of your seal is to immerse your prototype underwater, close it up and put it underwater. And then actually it would be great for you to add weight so that it doesn't just float to the top, and then leave it there for a period of time. Now, you can certainly do that as long as you put some type of coating over the cardboard. I know I've talked to a number of teams that are planning on printing. You know, they're doing a 3D print of their boxes. And again, one of the issues in printing with something like a hard plastic such as PLA is it tends to be kind of porous.
Yeah.
It's not that that robust. So we're still recommending for those teams that they think about putting, like a paint or a finish over the surface that will help to ensure that you're not just going to end up having water leak through unintentionally. Okay.
Mhm. And 3D printing is really, yeah, really difficult to get exact measurements, the tolerances on
Yeah,
each part.
tolerances
Yeah.
definitely
Oh,
become
we've
an
learned
issue.
that.
Yeah.
So,
So
so
I would actually recommend maybe don't do this box is big, 19 inches um by 8
by
point.
22.
Yeah, just do a small one that shows your concept is working. In other
Yeah.
words, just scale it way down so that you could show your concept on a small scale model. Does that make sense?
Yeah, we're recommending that you design your box for an internal volume that will hold two baseballs, right? Or, two apples, about that much size. So you can actually definitely bring your dimensions down a little bit. Um, in the drawing that you have that we're looking at on the screen, when are there any seals that you're planning to use around the lid and the base of the box to try and ensure that you're going to get a tight seal there? Have you thought about any kind of materials or design ideas that will improve or reduce the likelihood of things leaking?
We're thinking like the, those lunch containers that have like the kind of plastic seals around the edges.
Okay. Yeah.
We were thinking
Yeah.
of something like that.
And pardon me.
Like
That's
a
not a bad
snapware.
idea. That's a
Snapware
reasonable
with a
proof of concept.
silicone.
Silicone, that's what it is.
It's a silicone seal, like a snapware container.
Yeah, yeah. And I think that's a good idea, right? So now what we would like you to do as well, and you've obviously done a lot of research, look at the physical characteristics of this silicon. At what point will it start to soften up or even start to melt? Because again, one of the challenges we have is an extreme temperature variation. Um, the moon that the side of the moon facing the sun, which lasts up to 14 straight days, gets well over 200 degrees above 0 Fahrenheit. And on the dark side, it drops down to below that. And even though you're on for instance, if the astronauts will be on the sun facing side of the moon, if they go into the shadows of large rocks and that type of thing, there are huge temperature changes, right? So we don't expect that you would build out of, NASA grade materials for your prototype. What you've come up with is a good approach, but be prepared to share out what you would recommend we use to actually build the box itself. Okay.
And that becomes real important because we lost a rocket once because the O-rings didn't hold in extreme
Yes.
temperature on Earth. So do the research, would really help to figure out, well, what should that be for keeping our rocks safe? You just use silicon that you have handy, but do the research.
Absolutely.
You've done some great research already.
Absolutely. Now,
Okay.
let me ask
Unfortunately, I
you.
think we're going to have to go because the young ladies have to go to class.
Oh, okay. All right. Very good.
Okay, make sure you round off all your edges. So your corners should be round because the astronaut's going to have this with his spacesuit. And so round corners and edges. And we'll probably have about 20 or 30 of these containers. I need you to see if you can collapse your handles, at least when they're not being held, so that we could stack these boxes more readily. And and one of your pictures showed this. Think about how we would stack them and put them on, hold them in the space station too. So there's still a lot of things, but you got till
Absolutely.
February, the end of February. So, and you can contact me anytime, ladies. And I hope you have a wonderful, happy holiday season there.
Thank you.
All right.
There's the
Awesome.
rest of the team. If
Oh,
you
there
want to
they
see.
are. Yes.
Happy
Showed
holidays,
up, but-
everybody. Okay.
I
Okay.
hope you stay
Bye.
well and healthy. Bye bye. Thank you.
Bye, Flo. Bye.
We just
Bye-bye.
had
Nice
one
to
team
meet
flow.
Yep.
Okay.
Just
We'll
one
All
see
right.
you.
Yeah, okay,
I'll
guys.
communicate with you in a
Thank you.
Yeah.
via
Okay.
email, Flo.
Yeah. Anytime. Bye, Dorothy.
Bye.
Bye-bye,
Thank-
Flo.
Yep. Thank you, Dave.
You bet. Talk to you later.
Okay. Bye bye.
Let me